So we're gonna talk about quite a few equations, basically. Not quite a few equations, it's just several variations of Bellman equation that we have talked about. I think that equation basically was um, proposed back in 1957. I think so, if I believe the year is correct. So that's when actually the artificial intelligence was gaining quite a lot of fame and quite a lot of new things. And then McCarthy, the guy from MIT, he basically proposed the very first conference or workshop on AI, and then things started booming and everything. And so this equation basically has been playing a part in especially reinforcement learning quite a bit. So we're going to try to make sure that we understand the basic behind it. We're going to talk quite a bit about dynamic programming today also, where we will see that this equation basically is recursively applied. So a few scenarios where we are just going to expand basically our tree or expect max search, and then have a reward process, how the rewards are assigned at each state when we make a certain action from a state S and take an action A, and how we might land up in a new state, and then how Bellman equation plays a part in it. So we will basically unfold the tree to at least one step ahead in the future, and then see how Bellman equation plays a part in it. Because that's basically what is the core of the calculations or the value. Remember, we said that the values are all at the leaf nodes or the terminal nodes, right? Where basically the game is played. So what you do is you do recursive calculations and propagate the value back up at the root, so that wherever you are, basically the root is the start of the game. And that's where basically you look at the value and find out where to do or what to do next, which is in the best interest, or which maximizes the expected utility. So we're going to look at MTP, and then we're going to talk about how we can calculate optimal values. Okay, because in our search problems, we looked at the trees and then finding out the least cost path, right? But here, although it is very similar, MDP is very similar to Expectimax, but Expectimax did not have any reward process, or we did not see any rewards, right, at any node. We still have the chance nodes in here because the environment does play a role. And as I mentioned that, whatever action we choose, we are not 100% sure that we are going to get into an intended state or not. Okay, so we're going to talk about how still when there is randomness, this uncertainty, how we can get basically optimal values using two different methods: value iteration and then policy iteration. And then at the end, we will try to do a little bit of a comparison to see when does each method basically become useful in different scenarios. Okay, so a brief recap of the grid work, right? We said that we will start with a maze-like problem where the agent lives in a grid and the walls basically block the path of the agent, and the agent basically chooses a certain action, and then based on the action, there is a certain probability, or there is a probability distribution of where the agent might end up in the next state. Something like this. You see, we said that if the agent in a certain, is in a certain square, if basically if the agent takes an action, it's actually a noisy movement, because we said that even if the action to go north is chosen, there's not 100% probability. That's where Expectimax plays a role, right? There's not 100% probability that it will always go to north. Its foot might slip, left foot might slip, and it might just go west instead. Its right foot might slip, and it might go just east with some probability. And we said that a basic problem where we said that it can still take north, east, southwest, 4 different possible actions. And after taking the action, the agent, we are not 100% sure where we might end up. So there's still 80% chance that it will go north, but there is a 10% chance it might either go west or east, right? And then we talked basically about the part that is different from the expect-to-max search. We said that, when we get to the end state where the agent can exit, where there's a plus, 1, and I copied a figure from Google, the diamond, that's where the biggest reward is. That's where you can take the exit and then get the biggest reward possible, plus 1, or you might get into a negative, into a state where you basically end up falling in a fire pit. That's where you get the negative reward. And we said that there might be a terminal state. A terminal state would be to get into the square where you exit and you get the maximum possible reward. Or there might not be a terminal state where you just end up throwing your agent or your robot in a fire pit and it just gets destroyed. Okay, so we conduct multiple iterations. Not the simulations, I would say multiple. So the reason why reinforcement learning is slightly difficult, or it actually causes a lot of the loss of the resources, because you interact with the environment and then you learn based on the interactions in multiple iterations. And there are some parts your robot might just hit a wall or something and gets damaged. That's where basically a lot of the work basically is done. So we said that there is a small living reward at each step. At each step, just like Pac-Man, we said that every time we make a step, right, if it doesn't eat anything, there's a reward of -1, right? There's a score of -1. If it eats something, it eats a dot, there's a score of 10. So there is a small living reward. Every single step that the agent takes, there is a small living reward. And then there's a big reward, the sum of the possible, all possible rewards at the end. And our goal is basically to maximize the sum of the rewards. So every time we take a step, all right, as an agent in one iteration, what we do is, if we do take the next step, what is the value of the state? What does the value of the state mean? Actually, how much reward the agent will get from that, from that future step all the way to the end of the game. Okay, so that's the value. So our goal is to get into the state that will give us the maximum possible reward, all the way to the, to the end of the game. So that was the recap. So what we did was the extra 2 things in our MDP from search problems was basically the reward function and the transition matrix, right? So we have a 5 tuple here, or actually also the gamma 2. So we have gamma, which is the discounting factor. We said that, how far do we want to look in the future? Okay, gamma equals 1 means like you look all the way to the future, all the way to the end of the game, or gamma, how many possible next steps that you want to, look at. Gamma equals 0 means like only looking at the next step, just one step ahead. So gamma controls how far you want to, or you can take a look at in the future, and that also adds complexity in the game, because complexity in the MDP, because suppose that your MDP is continuous. You can do like something, you can remain on social media while being in the class. If you remember, we covered the class dynamics example. You can remain, you can keep doing something. There might be cycles in your MDP. So in terms of when there are cycles, gamma plays an important role to break that continuity and make sure there is always an end of the game. Okay, so what we do is we have set of states exactly the same as search problems, set of actions exactly the same as set of actions that was in the search problems. What we have is the transition, the probability. Remember in expect-to-max, we said that we are at a current state, and there is a probability that is associated with each of the possible actions that we can take in the next step, right? And there was a probability distribution, that there is a certain probability you might take, you might get into a certain state. There is a certain probability that you might get into a, another possible state. Or for example, if you're in a current position, you can take north, east, south, west, and then you can basically end up being in a new possible state. So there is a probability distribution that is associated with each of those states. That's basically very similar to expect-to-max that we had. And then we had a reward function. Basically, what does the reward function say is that if you are in a current state, S, and you take a certain action, okay, you will end up being in the next state S prime with a certain probability. And reward function basically says that if you take a certain action from a certain state and end up being in a certain, S prime, in the new future state, this is the reward that you are going to get. Okay, so we don't have a plan in here. We have a strategy or we have a policy. Okay, and there is a way. Basically, a policy is a recommendation. What we have is it's a choice of action for each state that we receive. Okay, so then we have the utility. Sum of discounted rewards. So and the value is basically the overall value at of the game. How much value that we're going to get basically from a certain state, the expected future utility all the way to the end of the game. And we're going to talk about how value iteration works or how this value is calculated. And there is a new thing that we talked about in brief details about the Q values. Okay, so we have the actual value, like the utility that you can basically be in a certain state, but you also have actions, the value that is associated with each action. What happens if you take a certain action? How much reward are you going to get if you take a certain action? And our job is to choose the best possible action that gives us the best possible, highest possible reward. Right? So we're gonna look at just like this one step look ahead in quite detail today. This is just like expect max that we were talking about. There's a maximizing agent, then there's a probability distribution over certain actions, right? And then there's there is a set of states that you might fall into after taking a specific action. The reason why we included the what is called the chance node in here, because as once again I'm saying that we are given certain actions like north, east, southwest for Pac-Man, right? Or go left or right or forward for an agent. We can take a certain action, but we're not sure where the environment will throw us in, will put us in, which is why we have the expectation or chance node in here. So we can take a certain action, and then there's a probability distribution. There can be multiple states where we may end up in. So that's why we have a chance node. So we looked at basically the class dynamics, MDP example. You can basically, stay, you can choose a certain action, right? So what we did was in the last class was that we had this very simple, class dynamics example that you can start with class 1. If you are interested in this specific module, you can go to, class 2, you can go to class 3, and then you can pass. And then there was a bigger reward that was given, basically, R equals 10. So that's the overall reward, the +1 in terms of the similar to +1 in the maze world, right? And then there were small living rewards, and they can be negative. That's okay because we will talk about how these rewards are also important in the game, but they can be negative. So what we did was with each arrow there was a probability distribution, right? There was a probability that was given that there was certain % chance that if you stay active in the class, you may end up being in class 2. You advance to class 2. There's a certain % chance that you might find it boring and you start using your social media, like Facebook or any other social media that you like. So if you remember in search problems, there were, well, mostly what we talked about that there is a heuristic. Somebody has given us the heuristic. Somebody has. So it can either already be given, that's called the policy. Like somebody gives you like, okay, here is the plan, here is the strategy, policy, you just follow that. Just follow that, a set of actions, and then you get the probability from there, transition matrix. But in real world cases, it's not usually possible to get that policy. You will have to do basically interact with the environment and get those probabilities from multiple iterations or multiple episodes. of experiments. That's where the reinforcement learning comes from. So right now, let's see that we already have been given the transition matrix. And policy iteration and policy evaluation that we're going to talk about is actually going to talk about these probabilities. Okay. So what we can add now from last week was that we did have the rewards, right? And then we said that the maximum reward was RT plus 1, gamma RT plus 2, plus gamma squared RT plus 3, etc. Look at this reward all the way in the future, and this formula basically was sum of k equals 0 all the way to infinity gamma RK t plus k plus 1. So what you do is you stay here in this state and you basically look at all the possible future possibilities where your game ends, and then you calculate the sum of rewards. Okay, so we looked at this game and we also looked at basically what's the role of gamma in here, but I will talk more about that in just a few minutes. We said that there are now two terms. Okay, maximizing agent basically is going to choose the best possible action, and we were using the max function, right? Max over q. What is the q? Q state basically gives us the possible action. So there's a value v of s. That's where we get the value. So something like here. We're at the chance node, and there's a certain probability that is associated with each of the possible state, and we just simply get the expectation. What is the expectation? It's just the weighted average, right? So on here, we're not sure. Even if we have taken a certain action A, the environment might put us in any of these next states, right? So we just get the expectation over this in here, okay, for a specific state. And then we just simply look at the possible actions and we find out what is the best possible action that we can take from here. And that's where we use the max. So that's the maximizing agent. So here we just talked about the expectamax, like expanded, expectamax. We have, we're doing a certain step look ahead in the future. So that's how we can create the entire tree and find out the value of the game using expectamax. But there are two important elements in this scenario. One is the value of the game, actual value of the game, and then there is a Q state. That basically is the expected utility starting out having taken an action A from statements and thereafter. All right. So we will be calculating the Q state and the V of S. The Q of S and A, Q star. By the way, star means basically the optimal action, the optimal policy that we have, the best possible action that we can do. And then V star is the expected utility starting in the S. So V basically is the state value function, and Q of SA is the action value function. And we're going to try to, understand in much more detail about how these quantities are calculated when we expand the tree like this. So far, so good? Any question, any confusion, anything? By the way, we haven't gotten into the derivation of these equations yet. So, good, let's warm up. All right, so what we did was, I think I'm gonna just open a few steps, a few slides from last week, from last lecture, to show you what I mean by the value function. Okay, so what we did see, we said that the value function is just simply, you look, so suppose that you're in this state, all what you do is you look at the possible, all future possible states, and from the reward possible big reward, you just simply propagate the values back. So you're expanding the tree or expected max search. Okay, and with Q values, you have 4 values at each state because you can take 4 possible actions, right? So value is, that's why I said the V of S is the state value function. So at a specific state that you are in, you can get that maximum possible overall reward, right? And then the Q values are actually 4 possible values. What happens if you take north? What happens if you take west? What happens if you take east or south, right? So then each action is associated with a value. And that's what we're going to talk about. These are the 2 different things. Initially, what the game scenario for this looks like is something like this in the first iteration. So before, there was nothing. You see here at K0, you simply have that board completely just empty with all 0, 0, 0, 0. But at the end, we know that the final reward is that. So in the next iteration, you see the values are actually being propagated back. The values are being propagated back all the way, and eventually it will just converge. Eventually, there will be a situation where in the new iterations, these values simply just don't change. So the value is propagated. Remember that from the leaf nodes, the values are being propagated up at the root node. So the root node is where you are at this moment, where the game starts. Suppose that you are here, or you're here. You can be in anywhere. You can be just dropped in any state, right? That is going to be your start game. So if you are standing here, which is your value. Yeah, it's going to be propagated from the lead node, from the value, from the node where the terminal states are. Then they're going to be propagated back. And then you see there are arrows also. So this chart is showing the value of the game, value of the game at each possible state, and then a possible recommendation, where to go. Okay, so that's a policy, value, and also the policy. So we will see how value iteration has implicit policy given already. You don't get to change the policy. You don't get to change these arrows, but they already are given or recommended implicit with value iteration. And there is an issue with value iteration. It is actually much slower than a few other methods that I will talk about in just a few minutes. One second. I think I lost all right. Okay, let me put it back on because I lost the view here. I won't be able to draw. Markov disease. Here. Okay. Okay. So the fundamental or basic idea behind Bellman equation are just simple. These 2 simple steps. Step 1: take the correct first action, and then keep being optimal from there. Just keep improving after there. It's very simple. And that's called the principle of optimality. It's called the principle of optimality, which Bellman equation follows. Basically, take the correct first action and then keep being optimal. And one way to do that is just simply dynamic programming, right? Simply divide the overall problem into smaller steps. Take the first correct step, and then keep applying that same optimality at every possible step, right? Something like this. Suppose that we are in again, maze world, and here is our little, Pac-Man, and its goal basically is to eat this dot. So there might be two, possibilities that might be given to this Pac-Man. Just take this action, get the reward of 10, all right, 10 only, and then what you do is these are all the steps, divide this into smaller steps, and apply the same principle of optimality for all the steps here and get an overall score of 100 here. Or you can go this way and take 20, reward of 20, but then get only the reward of 50 at all, cumulatively. So what you do is you just basically say you take first step and be optimal, and then apply the same steps and keep being optimal from there. So even if in the first step you're getting slightly lower score, but then you're applying iteratively, recursively the same principle of optimality to find out what's the best possible way all the way to the end of the game. And that's what we're going to do today, quite a bit. How we can expand and look ahead in the future and identify what possible, how we do the value iteration. Okay, so let's look at basically the state and action value functions once again. So all what I did is I just calculated the value of the game at each step. This is just a class dynamic example. Once again, that's the sleep. These are the classes, and then you have the bar. Okay. So what I'm going to do is the empty circles are going to be the states in our MDP. And then the third circle is going to be the action. Okay. So I converted bar into an action because that's under your control. Okay. So to add more control, okay, like agency control in the MDP, I just simply converted into an action. And let's see, let's look at how we can expand Expectimax into several steps in the future to basically get the state values and action values. Just like how on the board we saw some values, right, that were printed after several iterations. Let's see how those values are actually calculated so that it makes sense, what we're talking about. First of all, we basically, here for these arrows, we are given certain probability, right? We say that that probability is basically given by the policy that we follow, right? The arrows that we have. So let's see that the policy is completely random. There is no specific priority given or preference given to any of the states. So it's just like from one state, if there are two possible actions, it's going to be 50%, 50-50. If there are three, it's going to be 33% each, something like that. Okay. And then gamma, we're just looking all the way in the future, all the way to here. And all what I did was after several iterations, I just printed the value of the game. That's what you looked at the board. Okay. So what we do have extra now in here in the MDP is that we have small living rewards, right? These red one. And then we have the overall big reward at the end. And now we have possible actions. Like from class 1, we can study and get to class 2, right? And from class 2, we can continue studying and we can basically pass, right? So now we also have actions, possible actions associated with each of the state. So if you are in a certain state, you can perform a certain action and get to a new state. So all what I'm doing is adding a new notion in it by basically talking about, or by basically printing the possible actions that we can take. So go to the bar, right? And then we get a reward +1, study, then we will get the reward -2, study, then we will get the reward 10. And then we will see how we can expand basically these states to calculate the value, the expectation, right? Because you see the value function was the expectation, because we can take a certain action, But once again, the environment is going to put us in any possible situation that we are not sure about, which is why we are doing the expectation or doing the average. And then we have the Q value. So the reason why I'm putting pi in here, pi is basically a specific policy. And in this case, we're talking about pi completely random policy. We don't have a preference over here. Let's see, it's just like, to just stay or make this much more simple to understand what it is. Okay, and then we just simply, what we do is with the Q value, we do the expectation, we get the immediate reward. So let's go with the value. So for a certain state, okay, in here, the expectation is that we get the immediate reward. We have the discounting factor, and then it says that if I take this action and if I get into the new state, and we just simply get the value at the new state. That is it. And we just do the average. Okay. So in here, what basically is from class 1, we have this possible state and we have this possible state. And we are simply calculating the average over these two. Run it. Expectation, average. E basically is the expectation, or expectation in other terms is the average, weighted average. Okay, so let's expand that. I'm going to talk about what this E means, what the formula actually is. And this one, that's gamma. That's gamma, that's the discounting factor. Like how far you want to look at the view. So look at the view. So what this is, the value of the game, suppose that you're in this state, minus 1.3. There are two possible states that you can go into, right? Like study and get into the class 2, or just use Facebook, right? So you can be in two different states. What I'm doing in here is, for the value of the game, I'm just simply averaging over these two. And I have the reward, I have the probabilities. Basically, probabilities are given by the pi, right? The policy. And I'm just simply averaging those. And we can have the same thing for the Q state too. We can have the same thing over the actions, right? The action is the expectation, the reward, immediate reward that we have, and then we have the gamma, and then we have the possible action, next action that you can take in the next state, in the next possible one step look ahead. All right, good. Let's see how the state and action value functions are calculated. Suppose that you are in a specific state, right there, V pi of s, and you're in a specific state, empty state. Remember, I said that the empty circle is the state and the filled circle is the possible action, right? So if you're in a certain state, what you can do is take a certain action, right? Now, suppose that you've built a robot or something, right? And the robot can either take a left or right in very, very simple terms. So you're in a certain state, in a certain XY position. You can either take right, or you can or you can take left. Right? Make sense so far? Now the policy tells us, or gives us the probability that there is a certain probability at my current step. There is a certain probability I might either take a right or I might take a left. That's the policy. That's going to tell us. That is pi A given S. Right? Given that you are in a certain state, there's a certain action that you do. And this big A is simply either left or right at this moment, for now. To just remain very, very simple in the game. Right? So all what you do is you say that there's a certain probability that you take either left or right, and then you simply just multiply with the Q value. So we get the Q value. Remember those 4 possible values. If you take a certain action, you're going to get certain reward, right? Certain reward, and then gamma, and then the next Q value of the next possible state that you're possibly in. So what you are doing is very, very simple in here. All what you're doing is you're getting the Q value from here, you're propagating that back up. You're getting the Q value from here. You're calculating the average. And you're simply getting the possible action or the V of S using simply this formula. This is just an average. That's the expectation, Ronald. The expectation. We're just simply doing the weighted average, okay, using pi. So all what we're doing is getting the Q values for certain actions, propagating them back up, averaging them together, and calculating the value of, value of the state, given a certain policy, which is why I'm saying policy pi on there. Simple, right? You're in a certain state, you just average. And you can do the same thing with after basically taking a certain action, right? So suppose that you have taken a certain action. Suppose that I was standing here and I took a left. I took a left. And that now means that if I took left in here, I'm going to be expecting to just go left as a robot, or I'm going to be expecting my robot to go left, right? But remember, we said that the environment plays a role in there. There might not be 100% chance that your robot will go left. What if its foot, slips? It might go right instead of the left, right? So what you do is you have taken a certain action, let's say go left, and then the environment may put you in a different state. You might either fall, you might go left, or there might be another circle here on the right. You might just go right with a certain probability, right? You can be in any possible state from that step forward. So by taking a certain action, you have the Q value, and then the Q value for the next possible state is simply the reward, immediate reward that you get. Remember the small living reward, immediate reward that you get, and then gamma, and then simply averaging over these states, right? Make sense? So what we do is we take a certain action, we get an immediate reward, okay? And then what we have is V pi of S prime, which is S1, let's say, and V pi S2 prime in here. And even if we take a certain action, remember that there is an 80% chance that I might go north, there is a 10% chance I might go east, and there is a 10% chance I might go west in the maze world, right? We're just simply averaging them together in here. Sounds good? With the probability. And the probability comes from, this probability is basically the transition probability, the transition matrix that we have, right? So all what we do is we simply get this value up, and we average them together. We average them together, and then simply we add it with the reward. And basically, this is the average, right? This is the average, the sum, the inner sum. This is the average. We multiply with the discounting factor, and we add it with the reward, and we get the Q value. So now we get 4 possible Q values in the maze world, and we get 1 possible value for each state. Sounds good so far? Make sense? Okay. We can also stitch both of them together and get our value from one state to another, because that's what our job is, right? So we can stitch both of them together. And by the way, ignore this one for now, please, because it's on the right, and I just didn't put the animation correctly. So all what we can do is we can take this part, and stitch them together to get the value of the state by basically, stitching them together. There is a certain state that you're in. You can take a certain action. We average them over, right, together. And then after taking a specific action, the environment might put me in a certain state, and we simply average them together, and then we propagate the value back up. That's all. It might look really, complicated, but it's actually pretty simple. Remember, before what we had was summation over possible actions, and then here we had the value QSA, right? Only QSA. All what we did was we took the equation of the Q value and we plugged it in. So the Q values, remember, reward plus gamma transition probability times the V pi of S prime. What is the V pi of S prime? Is that if I am standing here, I took the action left, what is the value from that point forward? What is the value of the game from that point forward? That's the S prime, the next state. So, and then we can do exactly the same thing for the Q values too. So you see, what happens is, what this inner sum, this one, see, V pi of this prime, and we are averaging it. We are averaging them. So this smaller inner sum is actually this one. So we get, like, these are all S prime, set of S prime. We propagate the value back up. We average them together, right? We average them, great. And then we add the reward, immediate reward, with the discounting factor. And then we propagate them back up and we average them based on the pi. Because pi tells us what specific action that we can take, right? Pi, or the policy, is a specific recommendation. Remember, we said that pi is a policy that tells you what is the possible action or what is the best possible action that you need to take in a certain state. So that's the average. So the bigger sum is the average at the top, and the smaller sum is the average right here for specific states. Make sense? And for the Q values, we can do exactly the same. So for the small, now you see that the larger, the pi A of S becomes the inner average or inner sum, because we are averaging over the actions in here. Ronak. Pi gives you a recommendation. So what would be a best action that you take? So your policy has to be updated. So your policy has to be a set of best recommended actions from each state. So there are ways to calculate the policy. There might not be only one policy or one strategy, right? So that is something that is related to value iteration, policy extraction, policy evaluation. That's what we're going to talk about right after this slide. So that policy is basically evaluated and extracted based on the best possible actions that we can take. Right now, we are only trying to understand how we are getting these values from states to actions and how we are calculating the values of those actions and values of those states. Okay, so what we do is, so you see here, we're averaging over the actions, right? Or over the Q values. Make sense? Right here, we're averaging over the Q values. We're getting it all the way up in here. And then from the states, we're simply averaging over the probability that we have, the transition matrix, right? There is a certain probability that you might be in a certain state, S prime, right? In a set of certain states. That's what we are going to get from the transition. And then we're going to add it to the immediate reward that we're going to have and the discounting factor. So this is, once again, this may look very complicated, complex, but all what it does is, you see here, this one, this is you're propagating the Q values back up, and we are averaging them based on the policy that we have, because the policy tells us what possible action that we can take. That's great. And then you're just doing this too and averaging them together for this, and then you're propagating these two up again in here, and you are averaging them based on this bigger sum. That's it. It's very simple. It looks much more complicated, but all what we're doing is just iteratively applying this average function in here. Okay. We also have to make sure that these averaging or these formula, the formula for the state value and action value is correct, right? How we can verify it? Well, we can verify that the left side is equal to the right side. right, of the equation. So now suppose that I put basically the value of 7.4 for this specific state. Remember, the reward was +1 in here. The reward was 10 in here. There was a okay, what is the? I forgot what the probabilities were. I think the probabilities that I put. Yeah, I think there was a reward of 10, and then we have, yeah. So there's a 20% probability that you will get to class 1 from the bar, 40% probability that you will get to class 2 from the bar, and then there is a 40% probability that you will get back to pass. Now I calculated the value of 7.4. Now look at this formula. So we are at the state, right? Look at this formula and let's try to put the values in. Remember here for pi, what you can do is using pi from this state, you can either go to sleep or you can go to bar. Two possible actions. That means our pi is 0.5, right? Our pi is going to be 0.5. Make sense so far? All right. So there is one possible way that you can go in this direction and get the reward of 10, which is this term, 0.5, and get the reward of 10. But then when you get to the bar, there are three possible ways that you can go into other states. I think this was class 1, class 2, I think so. Something like that, right? So there is a 20% probability. So this is the immediate reward +1 that you get, this one. Then there's a 20% probability that you can go to class 1, and that's minus 1.3. There is a 40% probability that you can go to class 2, that is 0.4 times 2.7. And then there is a 40% probability you can get back to that state where you were. And if you add all of them up together, the answer is 7.4. I promise that is correct. So that means, Nathan.
But the probabilities could be different.
They can be. Yes, they can be. This is just a demonstration. I said that 20% probability. There might be 50% probability.
I'm saying for the known or like it's not in this particular case, it's 50% that we have to go to the action.
Right. Because I said that the pi is random in here, we're just assigning 50-50. It can be anything. It can be different. So that policy basically is updated at every step, every iteration that you take. So that's something that we're going to talk about in just a few moments. One thing we didn't talk about was we were saying that we're going to average over these, right? But our job is to find out the best possible action, choose the best possible action. How can we do that? Instead of using the average, we're going to do the max, right? We get the Q values, Q value in here, Q value in here, and then we will take an action that is going to give us the highest possible value or maximum. It's effectively. So what we are going to do is we're actually going to use the max over the possible Q states instead of just the average. So what Q is the same. Why? If we take a certain action, right? So Q is still going to use the average. You know why? Exactly. Because we can still take a certain action, but then we're not going to be in control over which state we're going to land in. Because we said that the environment might play a role, and it might just put us in a state with a certain probability. We're not 100% sure. It's just like expectamax, right? So with expectamax, we're basically, we can still take a certain action, but we're not sure where we will end up to be in. So with the Q state, we're still going to use the average. But with the value, because that the action is in our control, we're going to take a certain action that is going to give us a possible best or maximum possible value. So we're going to use the max function. You know what the complexity of this might be? So you see in here, so if we stitch them together, it's going to be something like this, right? And then there are certain states. So suppose that this is a very simple, graph. So for each state, we are looking at a set of other possible states, right? So that means we have s squared, right? We're looking at s squared. For each possible state, it's like a nested loop. For each possible state, we're looking at a set of other possible states that we might fall into. So the complexity is s squared, right? S squared in here. But we're also using a max function. So for each state, we're using a max function too. That means we are running a loop over a possible set of possible actions too, right? So that's another A. That's an A. So its complexity is going to be S squared A. So the value iteration is much slower because at every possible state, you do the complexity of S squared and A because you're updating your actions and policy gets implicitly updated. So I think if I bring to you the, okay, so let me just type this equation once again, just once again. Suppose that you're in this state in here, okay? You're gonna use a max function in here because you just want to get the, to take the action that is going to give us the best possible value, right? That's great. So for the action, what you're gonna do is you have taken a certain action, okay? You're taking a certain action, and then you're looking at basically the V star of S prime, right? V star of S prime, you're gonna get a value. So you're gonna get a value of landing in any state. So you can get the value, right? So the value that is calculated from the next step, which is great. But you're not sure where the environment is gonna throw you in, right? So you have to average it over the transaction matrix, right? You have to average it. And this exactly is expected max. We're just simply calculating the average, right? What additional thing we have in here is we now have rewards too. We're going to get an immediate reward, which is what we are going to put it in, plug it in, and how far sighted you want to be. That's the gamma. That's how it is slightly different from expected max because we have added reward and we added gamma. And plugging this value in equation 1 in here, the V basically gets the max of these Q values, right? And you know what the star is? Is the best policy. It's the policy that we have that gives us basically the best possible actions to take. So the star, every time we say, is the best policy we have chosen. No, A star, the star on A is a different. Okay, so here by star, we say that star is our best policy that is giving us the best possible actions at each state. And what we do is something like this with K, you see here. So every time there is an iteration, what we see is that initially, everything was just 0, and then everything just had to arrow up, just go north because there is nothing trained in here. After one iteration, you will see that the value iteration, it calculates by basically I have the discount factor of 0.9 and there's just like 20% noise. The living reward is 0 at this moment. Okay, so every time I do some do that value iteration, you see the values are changed plus the arrows change too in the value iteration because you know why? Because we're using the max function. We're using the max function, and now you see the arrows basically are changed and the values are being propagated. And there will be a point where the, I shouldn't say the game, or the scenario basically will converge, K will converge, and these values will not change anymore, and the policy will remain the same. So because we are using the possible set of actions and the states in value iteration, at the same time, it will change the value of the state, and it will also change the direction or give us the possible action. It is implicit, but its complexity is much higher than the function's basically policy evaluation. So with value iteration, what we're doing is we're just like we're having multiple iterations, and then at each iteration, we're identifying what was the best possible action, right? And we're identifying a possible policy. What if somebody gives us so that's a fixed policy. Basically, that's the fixed policy, because at each step, you're looking at different possible actions and you're performing a max over it, right? So that's the fixed policy. What if somebody hands you a policy and says, don't do anything other than what is given there? What if somebody just, gives you a policy that already has the arrows? That already has the arrows, right? Arrows given. And all what you do is, for each specific set. So in fixed policy, you look at all possible actions, and then you perform a max function. You perform a max function. Does that make sense? So you look at, like, in fixed policy, in value iteration, you look at all possible action, and then you perform a max over. What if somebody gives you that at each step, only take a certain action? What happens then is, you see, your other actions are gone, because at each state, you're only given a specific action to take, right? Does that make sense? No, Nathan? Confusing?
If you're given a set of actions to take, why are you calculating?
So in fixed policy, you're basically, you're looking at all, possible actions to take at each step, and then you're performing a max, and then finding out what's the best action from there, right? So that's a fixed policy, and you implicitly update the policy and find out the best action, right? But suppose that somebody just, hands you like a heuristic, and tells you, don't do anything other than what is given to you. Then that means that each possible step, now you're given an action, what action to take. So you basically are removing the max function, right? Because at each step, you're already told what to do at each step. So you only have just one action possible at each step, because you are given a policy already. So that's what we're doing is, in here, we have the possibility of all possible actions, like these, and then we are performing a max. But in here, with given policy, we are only given one specific action to take at each step. So we are basically removing the max over A, and the complexity becomes only S squared. But what if the policy is not great, right? But what if you're told the wrong action to take at each step? So there are different ways to evaluate the policy, okay, and then extract the policy. One way basically is to, you still take an action, okay, you're given an action, and then at each specific, like one step look ahead in the future, you evaluate your policy, how good it was, how good your action was at each step, and then take that action, record that, and then when the next time you take the iteration, you basically identify from the memory how good the next step was. If it is better to just take that next step, otherwise take another step. Because you record and you keep the values in the memory. So what we do is we evaluate the policy. Oh, by the way, policy evaluation, I just said that. Now suppose that you were given this policy that always go right. Is it a good policy? No, right? Because if you are here, it's telling you to always go right. What if you're given this policy? Always go straight, always go forward. And if you look at the map of values in here, the values of these states are actually much better than the values in here, if you were standing here. Now, suppose that if you were standing in that square, the green were 100, it turns out that this policy was not that bad overall, because you see here that that's 100 and that's 100. But it depends basically on where you're standing, right? And then identifying what would be the best step from the policy. So you evaluate the policy and then extract the possible best functions, best actions that you need to take. I think I might run out of time. So you see, before we had V star, right? Because we were using max. But here, when we are only given a policy, that means it's a V pi. And instead of action in here, we're just using pi, meaning we're just using a specific policy that is given to us. That's the only difference between the value iteration and policy evaluation. I wanted to get to the policy. So I have already mentioned the complexity or efficiency. I wanted to get to the policy extraction part, because what we do is I wanted to show you the policy iteration. It just like there are two steps. You evaluate the policy or utilities for some fixed policy. They may or may not be optimal, and you just simply improve at every step. Update the policy using one step look ahead with resulting converged but not optimal policy. I wanted to just go over that part a little bit, but the idea basically behind value iteration, policy evaluation, policy iteration, and policy extraction is simply recursively using Bellman equation. And then policy extraction, basically you evaluate the policy and then update your policy based on the best possible action by looking one step ahead. So you're recursively applying Bellman equation. They're all the same, basically. The equations behind all these different concepts are the same. It's just the way you evaluate the policy by looking at each step. Suppose that you're given just like one fixed policy, right? And then iteratively improvement by simply updating the policy. Value iteration doesn't allow us to update the policy by ourselves, but it implicitly includes the policy. For policy extraction or policy improvement, you look one step ahead in the future and then see what was the best from the previous steps, from the previous iterations, what was the best possible action that was taken. So you see here, we are calculating V pi of k plus 1, right? And that is a reward of a current pi of s prime plus gamma. That is the V pi of k, meaning the k, so k can be from 0 to how many iterations that you have, how many times you run basically that simulation, or you make a robot take the experiment. All what you're doing is calculating the value for the future step. You're just getting the value from the previous step. And then see what was the value. When you were at this state in the previous iteration, then you saw how good it was, how good the policy was in the previous step. And from the previous step, like one step look ahead, see how good every possible state might have been. And then pick up the arg max. Then the max, because you're looking at the one step look ahead, look at the arg max and find out what was the best possible action. What happened when I took this action in the previous iteration, right? Because in one iteration, your robot at a certain step might go left, right? In another iteration, your robot basically at the same step might go right. So now you have both the policies because you have multiple iterations. So from the previous step, you see how good it was to go to either left or to go right, and then just do the arg max. That's just a policy iteration. Everything is the same. The Bellman equations are just the same. Okay. So I wish I had more time to go over basically this comparison. Value iteration. What is the difference between value iteration and the policy iteration? Well, one thing we have seen that the complexity of value iteration is S squared A. And policy evaluation, we can remove the A. Okay. So okay, so we're going to end, and we're going to continue. We're going to continue our lecture on reinforcement learning from next week. But you will see there will be, so every every iteration or every real problem that we're going to solve, we're just going to apply the